Hi everyone, thank you for joining us for our Introduction to Static Motor Testing webinar. I'm Meredith Kenton, MEGGER's Digital Marketing Specialist, and I will be moderating today's presentation, as well as helping or reading questions to Leslie at the end of the presentation. On the right-hand side of your screen, you should see a panel that looks like this one. We ask that you, no, you're good. We ask that you submit your questions throughout the presentation here, and we'll do our best to answer as many questions as possible at the end. Don't worry if you don't get an answer though, Leslie will answer your question via email after the presentation is over. And I already mentioned her, but today's presenter is Leslie Reed. She's been with Megger Baker for almost 22 years. And if you have any questions specific to these motor testing applications, I ask that you email her and not me. And on that note, I'll give it over to Leslie.
Thank you, Meredith. Again, I appreciate being able to present to you all today. This is a continuation of a webinar basically that we did last week. First of all, a little bit about myself. I've been in Northern Colorado for over 30 years. Originally came in as a software developer for the U.S. Forest Service. Actually, they do use computers there. And so I was programming computers for timber management there. Spent 3 years as a mathematics college instructor. And then I've spent 16 years as software engineer for Megger Baker Instruments. I'm mostly responsible for the code that goes into the AWA. And partly with the DX and the desktop software there, and some of our dynamic testing. So after 16 years being in a cube and wondering what you all do with our instruments, I got the opportunity to become application engineer and actually speak and help people using our instrumentation to solve issues. So I've been in the last 6 years as application engineer and worked into being a technical trainer there for Megger Baker Instruments. Today we want to look at specifically static testing. So I know Drew last week, and I actually would like to have a show of hands if you can raise your hand if you actually attended the webinar last week with Drew. See how many people are awake here. Yeah, there we go. We got some hands, several. Seeing several people. Looks like a good portion of you guys were attending the webinar last week. I appreciate that. And so I'm going to expound on what Drew presented there. He presented two topics, being dynamic and static testing. And today we're going to look at static testing. So outline of this webinar here would be to see why we doing this kind of testing, why perform static testing. We're going to look at small amount of motor construction that's pertinent to testing statically. We're going to look at the causes of insulation degradation, and I know Drew went through a couple of slides there of why insulation degrades. We'll look at that again today. And then we want to look at how static testing finds insulation weakness. So the tests that we'll highlight today will be the winding resistance tests, the DC tests, which include insulation resistance testing, the MEGGER test, the DA, the PI, high pod or step voltage testing, and then finally we'll end with surge testing. So why test? And if we look at the view of this setup here with these motors, a lot of dirt and dust and contamination on them would kind of be our first indicator that we might want to test to see where that insulation is on its life curve. So to begin with, I know Drew showed you a graph similar to this one here. Talked about the bathtub curve and the probability of failure, that when you first receive a motor in and you put it into an application, we expect a high probability of failure then, the infant mortality. Things due to manufacturing defects and rework faults there become apparent when you fire the motor up. Maybe just how the motor was put into the application. It wasn't aligned properly. It wasn't connected properly. All those things play into why there's a high probability of failure in the beginning of time. So this becomes a good time to test. As you receive that motor in from the shop, or a brand new motor, go ahead and take it out and static test that motor. Make sure that its insulation system is good. It's nothing worse than having a motor fail on you. You go to your warehouse, pull out that motor that you have sitting there ready to go to put it in place, and now you've spent 2 days, 2.5 days doing the swap out, only to find that that motor was not good. So it's important to test during that infant stage. When you receive that motor in, when you go get it from the warehouse, make sure you test it there. You get a baseline, put it in to the application, test from switchgear. Now you've got a baseline for that motor. As it goes into its useful life, we expect low probability of failure at that point in time for a certain amount of time, and depending on its environment and how we use that motor will depend on how long it lasts in that useful life period. So we're going to test periodically through that time period. We're going to test maybe once a year. We go visit that motor and see where it is. And as we do our testing throughout the years, we start seeing signs, the trending that it's nearing its end of life, and that's when that probability of failure is going to increase. And we want to know when that happens. So we're going to do testing during all phases of that motor's life. We saw a little bit of surveys that have been done as to where motors fail out. Most often in low to medium voltage motors, we're going to see bearing failures as being the highest. The next highest will be those stator failures. So static testing is going after that stator failure, the 26 to 36% in medium voltage. If we got high voltage motors, something greater than 4160, stator failures actually go up. We're at higher voltage. We put better bearings in it. So their failures of bearing related goes down, motor failures go up. So again, we have an application. We have a motor right at the center of it. And if our motor has a problem, then we have all kinds of technologies to try to diagnose that problem. We have vibration, and as Drew covered this last week, vibration that covers a lot about what that application is doing. It only sees a small amount of the motor though. Things like bearing issues, misalignments, we're going to see that, how it affects the motor through vibration, but it's not going to tell us anything about the insulation of that motor. There's oil analysis, there's thermography that actually does cover some issues with motors. We can shoot the switchgear, the junction boxes, looking for high hot spots, high resistive connections that are showing up that we can fix and give that motor better power. And then there is electrical testing. And again, we get those two sides of electrical testing, the static and the dynamic. And today we want to cover static, but I'd like to kind of point out that the dynamic and static don't replace each other. They are complementary to each other. Hence the yin and yang of the circle there. So to understand this, here we have the life curve that we've seen last week, where we start out very high dielectrically. So we have the breakdown voltage is our y-axis, time's moving, and the x-axis. And as that breakdown voltage, brand new motor, barring any kind of manufacturing defects, has a strong insulation system. What's stamped on the nameplate of that motor is its voltage rating as to where it's designed to run at. It is not necessarily a rating at how high that dielectric strength of that motor is. It's much higher. We have to build in some time into that motor, and so we start out at a very high dielectric strength. So the numbers you see there, 28,400 volts DC, copper to ground, copper to copper between turns is 16,800. This is for a 460 volt motor. So it starts out much higher than bus voltage. But as we know, as that motor starts to be used, you put it in service, it starts to age. So static testing is going to help us determine where on that insulation system that motor is on this curve. Static testing directly evaluates the insulation of that motor. Whereas with dynamic, again, we may have this difference between A and B motor, and what makes them different are factors that motor may live in, the environment that motor B lives in. Perhaps it's seeing unbalanced power, or high voltage, or too low voltage. Maybe we're overloading it. All those factors cause that motor, will shift that motor onto a shortened curve. So dynamic motor monitoring helps us determine which curve that motor's on. So again, if we have harmonic distortion, we're going to see heating in that motor because of it, and it's going to start destroying that insulation system faster. And it'll be time at that point, if you discover you do have high harmonics or high imbalance or low voltage, at that point in time, you take it offline and you test it statically to help determine where it is on that life curve with the end of life in respect to its end of life. So let's look a little bit at motor construction. Here we see a stator that has one piece of slot cell aligner, Nomax more than likely, laid into a slot. This guy's got his work cut out for him here, as he has just begun to lay in the coils. So let's talk a little bit about what kinds of coils and how the construction of the motor works. So we're going to focus here mostly on AC squirrel cage induction motors, which represent 90% of all motors out there. They're low cost, they're rugged in construction, they require less maintenance than those DC motors, widely used in all kinds of different applications. So we can see up in the upper right hand corner here, we have a motor where the rotors have been partially pulled out. And so the rotor there has no windings on it. Its construction is of a core center with copper bars or aluminum cast aluminum bars poured into to a casting there to form the bars. So there's actually no windings that we can test there. So primarily what we're going to be looking at with static testing is only looking at the stator insulation. So insulation between the turns that's on the wire itself and the insulation that's laid into the ground wall or the slot of the motor is actually where we're going after here. So windings can either be random or form wound. So here we see a cutaway of a motor that is a random wound or mush winding. Close up there is it's just the coils are laid down, and in the coil the turns are not formed in any kind of order. Turn 1 might be right next to turn 15, or turn 5. It's random. It's different for each motor of the same type that's constructed. So we have random alignment there in the smaller motors. With more voltage, higher voltage motors, we go to a form wound, where attention is very much, a lot of attention is paid to making sure turn 1 is right next to turn 2, next to turn 3, next to turn 4. So what they're trying to do there with this type of construction is to mitigate the voltage drop between turns. And this voltage drop between turns occurs in motors at startup. So at startup, contactors bounce, we get a high voltage spikes that cause a nonlinear drop of voltage across the windings. And this nonlinear drop means that between turn 1 and turn 2, there's going to be a bit of a voltage drop. But it's less of a voltage drop than between 1 and 15. So that's why the form wound coils are used in the larger, higher voltage motors. And it provides consistency. Usually hot spots will form in a consistent manner with a form coil, where in random it's random. So why we're concerned about that is because of the high voltage spikes creating this nonlinear drop of voltage across the windings. causes stresses that turn to turn insulation, and that's what we're concerned about. So factors that lead to insulation failure, to begin with here, I'd really like to do a simple definition. So insulator are materials that impede the flow of electrons from one molecule to the next. So here in the pictures we see on the left, the glass insulators that were used at one time to in our power distribution system to insulate against the lines that went through there. We've used, on the right, you see a power cord. This is the power cord we send out with the testers. Having the plastic rubber coating on it would be our insulation there. And then, of course, in the middle there, we see that motor with the slot cell liner, the Nomax being the insulator. That's our ground wall insulation that we're looking at there in the center picture. Conductor. So we have insulators and we have conductors. Conductors, we've settled out on copper as being hits the price point and is a very good conductor. Gold and silver would be good too, but a little expensive. So there we see coils of wire ready to be laid into to a motor. And again, the definition of that conductor is that material that permits electrons to flow freely from one particle to the next, as well as with insulation, it impedes that flow. So we've got material that impedes the flow of electrons. We've got material that allows the free flow of electrons. And then we have this relationship between them. And actually, it's a characteristic of the insulator that defines the maximum voltage difference that can be applied across that material before the insulator collapses and conducts. So we're interested in where that breakdown voltage is, or at least, is it in our view? Is it at the voltage that we're testing at? How does our motors hold up to that? So breakdown voltage we're very interested in. So if we were to have two conductive plates here, and we place the insulator in between, and then if we were just to raise voltage up until at some point that insulation breaks down and becomes a conductor. It collapses and conducts at that point. So again, dielectric strength of our motors, as I stated earlier, starts out very strong. Here we have NEMA MG1 that states that the wire, the magnet wire that goes into a 460 volt motor, should be able to withstand 6,000 volts AC. Let's convert that to a DC voltage at 8,400 volts DC. That's just the wire itself. Now then, let's look at our ground wall insulation. So that's the insulation here. We see, we pointed out here, the slot cell liner here, which would be our Nomax. That is rated at 20,000 volts DC. So if we add those two together, we take the coating on the magnet wire, 8,400, plus the Nomax, or the slot cell liner, at 20,000. That gives us 28,400 volts DC combined insulation to ground. So that's where those numbers come from at the upper left of our graph of our life curve. And this curve is shaped in a very specific way. It looks like we start out very strong and we have this expected time period here of a long life. But as we put that motor to work, I mean, the first thing we're going to do is start it, and that's one of the hardest things you could do to your motor intentionally, is to start it, and it starts degrading at that point. But once the degradation of that insulation reaches a certain point, it becomes very rapidly deteriorating at that point. So the places that we're concerned about, of course, is when we get to bus voltage. So if our dielectric strength, our breakdown voltage, becomes lower, 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 and lower, and at such time that the dielectric strength of our insulation falls below bus voltage, that's when we have catastrophic motor failure. That's when you get that call at 2 a.m. on the vacation day that you've been waiting for. You get called back into work because that motor failed in service. So what's causing it to degrade over time? That's what we want to ask here. So here's our factors that lead to insulation failure. IEEE 101 mentions the 10-degree rule here. So for every 10 degrees rise or increase in temperature of the insulation, the rate of insulation degradation is doubled, or we're halving the life of that motor. So what's causing heat in our motors? There's a lot of things that cause heat in the motor. Contamination. So we have the chemicals deposits on windings that actively attack that insulation. Such things as, depending on the environment that motor lives in, could be acid, caustic, even the grease that you may be putting on your bearings could be attacking the insulation. Some contaminations also lead to thermal insulation. So you're at a cement plant or a coal plant where that fine dust coats the windings. It's like putting a blanket on that motor. Plus the contamination there as we blow air over it is a form of erosion that occurs on the insulation. So abrasive wear of insulation due to the impact of airflow. And moisture. Moisture is a big issue. And we'll talk a lot about moisture when we talk about the DC tests. Mechanical, we get movement within the windings at startup. We get the thermal growth of materials as the motor heats up very rapidly. Copper expands at a different rate than does the iron core or the insulation. Over voltage spikes, high voltage surges caused by lightning, switching, VFDs. These voltage spikes have been recorded as high as 4 times bus voltage. Power quality, and Drew's going to spend a lot of time on power quality next week when he talks about dynamic testing or motor monitoring. So power quality, over voltage, causes the iron core to heat, and we get heat in from the middle of the motor out. Of over voltage, under voltage causes current. It makes it draw more current in order to produce the same amount of torque. So it's going to cause heat, voltage imbalance, distortion. Both cause heat in the motor, is why we're concerned with those. Corona and partial discharge. Again, especially higher voltage motors, we get the partial discharge. That's discharge of electrons there in a void of the insulation, causing off-gassing and a caustic chain of events to the insulation at that point in time. Load related, overloading. That is key, and a lot of times as a motor, as you're caretaking your motors, you're responsible for them, but the operator it has a different set of measurements. He has to get his product out, so overloading becomes quite an issue, causing higher heat in that motor. Misapplication of that motor, whether it's in horsepower, you got the wrong size motor there, or the wrong NEMA design for that motor. So again, looking at an application, what are the startup torque requirements for that application? Making sure you have the right motor in that position to deliver what you're asking of it. Frequent starts and stops. Frequent starts, again, we have to put protection systems around our motors because they're dumb and don't even know their own nameplate. In other words, they will keep trying to do what the load is telling it to do until it can't anymore. So a motor is going to keep on trying to do it. So we put protection systems around it. We put protection systems around it during startups, during normal operation. We should also put protection systems around to lock out operators if they've been started too many times within an hour. It's causing higher heat and can cause rotor damage and insulation damage. Startup and shutdown is a big piece of wear and tear on the motor. Frequent starts, we just talked about. Voltage spikes as high as 4 times nameplate. The inrush current that occurs there can be up to 10 times full rated current. Coil movement, it's at the startup. It wears away at that insulation, and you put a layer of grease and contamination of that coal dust or cement dust, and we get coil movement. Again, we get the erosion of the insulation. And the last one here we want to look at is the latent manufacturing faults, the voids in the insulation, nicks, inconsistency in the way the motor's put together, mechanical weaknesses, improper lead labels lead us to have faults. So all those lead into something we need to consider as to what's going on with that motor. So these are the factors that lead up to failure, insulation failure, or degrading the insulation. Here we see the actual failure modes of the motor. So we get turn to ground. So that's between a turn and the ground wall, where the insulation there has been compromised and is now less strong than we'd like. So this is where we spend a lot of our time with DC tests. So the MEGG test, PIDA, and the HIPOT test all give us that turn to ground information. The other three there are copper to copper type of failures, whether it's between two turns of the same coil of wire, or whether it's between two turns of two different coils of wire, or whether those two turns are between two different phases of the windings. So again, what we're interested in here is evaluating the dielectric strength of insulation, whether it's from turn to ground, turn to turn, coil to coil, or phase to phase. So we have been research paper from General Electric has told us that high percentage of electrical stator failures start as turn to turn. Most will fail to ground in the slot, and some phase to phase, but the root cause is that turn to turn failure. So if we had a way of identifying turn to turn failures, then we're ahead of the game in finding or seeing where that motor is on its life curve. So turn to turn insulation is the weakest part of that insulation in the motor. So that's why most failures begin as turn to turn. It is the weakest link. Chemical deposits break down the insulation. All that list of stuff we went through, those two slides, work on that insulation. Movement from the startup rubs the turns together, causing wear and damage caused by the winder. And additional turn-to-turn voltage stresses caused by high voltage spikes. Startup for the line operated motors during normal operations for VFD. As the VFD, the variable frequency drives, switch, it's causing these voltage spikes in that motor. So here's a video I wanted to show you guys of the turn-to-turn movement. Bear with me while I figure out how to do that, because all of a sudden I forgot. Here we go.
How important is it to test turn insulation? At General Electric, D.E. Crawford used high-speed photography to investigate motor failure. High currents, such as those encountered during starting or stalling, produce strong magnetic fields. These magnetic forces push and pull the motor windings. This motion, along with the differences in thermal expansion, wears away the turn insulation. A turn-to-turn short caused by wire insulation wear is the beginning of the end for many motors.
So as we see in that video, we have quite a bit of winding movement, almost looks like a heartbeat. And I know it's been slowed down so that we can see it with our eyes, but that's quite a bit of movement to consider. Now, consider that with, again, a grease-soaked winding with contamination buildup on the outside of that with dirt and dust, keeps all that heat in, and every time that motor is pulsing, we're rubbing those windings together, and that's where the erosion starts weakening that insulation. So motor Motors see high voltage spikes during opening and closing breaker operations, VFD high cycling frequency. So we've gone to, in order to kind of talk about this, to go to a per unit volts. So when we talk about a 480 volt motor, a per unit value there would be take 480 volt, divide by square root of 3, multiply by square root of 2, we have 392 volts per unit. So if we say that the worst case spike is 5 per unit, that would take that 5 times the 392 to get to 1960 volts during starting. So this is for a 460 volt motor, which is where we would recommend testing that motor at. Roughly that 4 times live voltage. So motors don't particularly fail during operating, where they only see a few volts per turn difference. But every time that motor's power supply switches, it can see those spikes as high as 5 per unit as a result of the fast rise time and the inductive kick response as we start that motor. So papers have been, studies have been done to see how high these voltage spikes are. Here in this paper, I've kind of got the highlighted areas there. The highest recorded surge was 4.6 with a rise time of 0.5. Magnitudes really usually are between 0.2 to 0.6 on the rise time. Here we see stator winding insulation has surge strength in the excess of 5 per unit with a rise time of 0.1. So voltage spikes can be as high as 5 per unit. This kind of studies and others kind of help us to form where we want to take our voltage to in doing our testing. So initial shorting happens often in the extensions. That's part of the motor. The windings come out and back into the stator bore. Failure to ground, of course, is in the slots. But in either case, when the dielectric strength falls below operating voltage, the turns will fuse together. And when they fuse together, then we get this high heat, I squared R, so we get an increase in current. Then we're going to square that to get to the heat. So it gets very hot very quickly. And according to IEEE, the welded fault will burn through the slot cell liner within 15 minutes. So you have a very short amount of time before this catastrophic failure occurs. So typical steps to motor failure. We'll go through the first one is that we start very high dielectrically. Then we put that motor to use. So it sees normal aging, was thermal, chemical, mechanical. Dielectric strength falls below those level of the switching surges. Arcing occurs during the motor startup. Insulation deteriorates much faster at that point. Then the dielectric strength falls below operating voltage. The short fuses together. We get a transformer action that, because of the AC nature of the AC power, causes a high induced current and high heat, and then we get rapid failure at that point. So the idea with this kind of testing is to catch it here at step 3. We're going to set our voltages and our parameters at this level where those switching surges occur at. We set it at that level so that we get warned, we get a heads up, we get a predictive nature out of this type of testing. So let's relate that to our life curve. So here we have our life curve. Our dielectric strength starts out very strong. We put it to use. It sees that chemical and mechanical thermal degradation of the insulation. There's our bus voltage. And here, this represents our switching surges as to however high they're going. And at that point, that's where we're going to set our test voltages and our parameters. So our step 3 of the previous slide, we're putting our magnifying glass right here, setting our test voltages here so that we can catch it as that motor falls into the arcing voltages that it sees during startup. So it gives us a heads up that this motor is in trouble and we need to take action. So the way that we're going to do that is through static testing. It finds the weaknesses. So again, a definition here is we're going to measure and track the electrical properties of the winding circuit in an effort to determine its health and reliability while the motor is de-energized. How? We're going to do it in two ways. We're going to do low voltage testing and high voltage testing. So low voltage testing is going to be measuring specific electrical parameters at or below nameplate voltages to determine a change in electrical circuit properties. So here we're talking about our winding resistance, copper resistance. We're going to do our MEG test. Our MEGGER test will be performed as considered low voltage, along with the DA and PI, which is the first minute of those is the MEG test. And here we're just looking for changes from past data. From the last time we tested, maybe our megohm value was at 5,000 megohms and now we're down at 1,000 megohms. That's an indication that something's going on that we need to pay attention to. High voltage testing. Then we move to high voltage testing. And this is where we're going to perform the high pot or surge test and surge test, testing motor insulation at a voltage level similar to those that the motor encounters in its normal environment to determine the integrity and the reliability. So this is where we're picking up that reliability piece. So it helps us determine the reliability of that insulation system. Again, it helps us to define that insulation condition with respect to its end of useful life. So as we move through these tests, put your reliability hat on and look at it from that perspective as we go through the tests. The equipment that we offer that performs these tests, whether you're troubleshooting, whether you're looking at quality assurance, your motor shop and making sure that your work is good, predictive or preventative maintenance programs. All these testers work for those situations. So we have the AWA here on the left, the DX is a manual run instrument here in the middle, and then the Power Pack, which either one of these two instruments can use to again raise the voltage on up higher for our bigger motors. So the AWA itself, it is an automatic tester. It comes with at this point we are producing it with Windows 10. In the past it's had 7 and XP embedded. It does have data storage and access database. It's networkable. Test voltage is 2, 4, 6, and 12 kV, and has the test capability of the coil resistance, insulation resistance, DAPI, high pot, and surge. So we see here the 2 or 4 kV is this size. We get a bigger size for the 6 and 12 kV testers. The DX series is a manual tester, so you're pushing the button and ramping the voltage. Does have data storage in it, testing voltages 4, 6, 12, and 15 kV, and has a bigger range of test capabilities, so resistance, capacitance, inductance. It will do a rotor influence check, insulation resistance, DA, PI, high pot, and surge, and we also added PD on surge, where we'll take the high frequency content off the surge waveform and quantify that in millivolts to ascertain whether or not you have PD activity in a motor. So here's the testing parameters at a high level view. Resistance, we're going to be looking at imbalance, which would indicate a high resistive connection, or we have improper winding connection internally. It could be short circuiting. If it's a hard short, we'll see a resistive imbalance. Inductance, again, follows kind of what resistance does, and it only performed by the DX. Is an indication of winding imbalance due to improper connections or hard shorts. Again, we're looking for balance between the 3 phases. Capacitance, we get one number, and in that one, we're going to trend over time. And if you have an increase in surface contamination, we'll see that as an increase in capacitance. Oftentimes, we'll also see degraded insulation, the elimination of insulation in older systems. Then we move into our DC test, which is our insulation resistance test. If we have a low MEGGER value or low MEG value, that's an indication of significant thermal degradation. It could be an indication of contamination. Moisture is influenced by this number is influenced by moisture. So again, we want to take that in consideration, temperature and moisture with this number. But if we have a low MEG value, that's indicating something to us here, that we have issues in that motor. An insulation failure, that would be an overcurrent trip by our tester. This is where the insulation, or current rapidly increases during the test. we're going to shut that test down and report to you an insulation failure there. Or if we detect an arc, that would also be considered an insulation failure. So that's insulation breakdown at that test voltage. Indication of imminent, it's coming. So if we're at a higher voltage when this trips, then that's an indication that we have a compromised motor and it has imminent failure. Or it could be existing insulation failure. It trips at a low voltage, maybe it trips on the MEG test. That's an existing insulation failure. You have no time with that one. Also with insulation resistance, specifically the step voltage test helps us out here, is a nonlinear response in current as we raise voltage up. And this is an indication of insulation reaching its end of life and contamination near its exposed conductors. Surge testing, we got erratic wave. That's the shifting of the wave as we raise voltage up. That's an indication of turn to turn or copper to copper insulation issues. Wave imbalance, that would be comparing one phase to the other phase of the motor. Again, this can indicate problems in the winding process or an insulation failure. And then partial discharge is also on surge. Again, indicates excessive void formations, internal deterioration of insulation. So we're going to quickly run through these tests. And I'm sure I'm going to raise more questions than I answer here as I move through them. So first one here I want to talk about is the line-to-line resistance. Measured resistance, usually in the order of milliohms. So it's vital that we're able to measure very small resistance accurately. And we're looking at a phase-to-phase resistance of a motor, and it depends on the size and design of that winding. And when we test three-phase motors, we're going to look at a resistive imbalance. So we're going to take the three measurements phase-to-phase and perform an imbalance calculation on it, and then evaluate that number. Temperature also affects resistance directly. As temperature increases, coil resistance increases. So we're going to use a separate set of leads on the tester. We're going to connect up the leads to the motor. And then we're going to look at the resistance between lead 1 and 2. So we issue a current, and then we're basically measuring the voltage drop across the resistor, the windings, and that gives us that accurate resistance measurement. So it will be a phase-to-phase resistance. So we take those three numbers that we're going to get, and then we perform an imbalance calculation. We do that in two ways, and both testers can do it either way. Whether we take max minus min divided by average or the max deviation from average, either way we're looking at probably an imbalance of 3 to 5% that we don't want it more than that. So in field testing, we're looking at high resistive connections because most likely you're testing from switchgear. We got improper connections, loose connections can give us an indication of imbalance there. Quality or post failure, again, we're testing at the motor in this situation. There's number of turns per phase variation, diameter copper variation. Could find turn-to-turn shorts if they're hard shorted, and finds opens. So once we find a high resistive connection, that gives us an opportunity to improve the power quality that motor is seeing and set it on a better curve. Next test that we will proceed with are the DC tests, and the DC tests include the MEGGER test, the PI, the polarization index testing, DA, which is dielectric absorption testing, high potential testing, which would be conventional high pot, step test, or a ramp test. Here we're going to apply various methods of applying voltage to the system and seeing the reaction through the current, leakage current that occurs there. So as we ramp our voltage up, depending on how fast we ramp, the faster we ramp, the higher that charging current is. And the reason why there's time involved in these tests is because we want to get away from that charging current. So we're going to hold our voltage steady. We ramp, hold our voltage steady. And as we hold voltage steady, our current then should continue to drop. And it comes through and it goes through this polarization current phase till we get down to our actual leakage current. So that's why there's a time consideration with these tests. We're waiting for some time to pass to get through so we can measure the current we're interested in, that leakage current. So we have, let's move through these tests and see what they're looking at. So MEGGER test, minimum acceptance criteria, basically is what you're looking at. We're wanting current stability here. So we're hooking all 3 leads up to the motor. We're going to energize all 3 phases to the same potential. So the only difference it sees is between ground and the potential of the winding. It can't see any differences between turns because they're all at the same potential. So we perform this test, we raise our voltage up to our at or near nameplate. Here's a chart that suggests what voltages we should go to for a MEGGER test. And so we bring it up to that voltage. We're going to hold for 1 minute and then we take our reading. So we're supplying the voltage, we're measuring current, we're going to calculate our MEGGER value, and then we're going to temperature correct it. So we're going to temperature correct, applying that test potential for 1 minute and temperature correct that value. And then we're expecting that value to be something higher than what we see here in these charts. So again, IEEE gives us guidance there as to what we should set our minimum MEGGER at. And we're going to take that minimum MEGGER, or that value that we measured, calculated, and corrected. We compare it here to the value you enter. A little bit about temperature compensation. There is 2 different methods in IEEE 43/2013, depending on the type of winding you have. And our products are able to allow you to choose which temperature compensation method to use. It's important to temperature compensate, not only for trending of the data from year to year, but also as a minimum. We're looking at minimum values as our pass-fail criteria, and that minimum MEGGER value is set at 40 degrees C. So we need to correct our measurement to that in order to compare the 2. We're also seeing those effects of humidity in this test. It causes that current to oscillate. So it's important to understand what resistance testing can and cannot find. It can determine if a motor has failed to ground. So if we fail this test, we have a failed insulation system, a ground wall insulation system. It can determine contamination levels. So if we have that low MEGGER value, that indicates to us contamination. We may have surface leakage. Again, we may want to consider that at the time of test, did we have a lot of moisture as we were doing that test? It's also important to understand what it cannot do. It cannot determine if a motor is suitable for reliable service. It can't find turn-to-turn faults or opens or face-to-face faults in the way that it's performed with these testers. We move into the PI and DA, which is the first minute of those is that MEGGER test. Here, what we're looking for in letting time pass is that our dipoles in that insulation are randomly aligned. As we put a charge to that insulation system, those dipoles align. And as they align, that's electron movement. So our current stays high. And as they align, that current begins to drop off, meaning our having the effect of our resistance increasing during this test. And we'd like to see that happen. So as a way of pass-fail criteria, we take a ratio of the 1 minute insulation resistance, we divide that into our 10-minute insulation resistance value. For a PI ratio, the dielectric absorption test is a 3 minute over 30 second, and there are also various other times that IEEE would suggest for us with these 2 tests. So we get a value out of that PI ratio. We'd like to see IEEE standard being greater than 2. A lot of times for installed motors, people go by a common rule of thumb being if it's greater than 1. Again, what does it mean if we have something less than 1 here? It means that our current stayed high. It didn't come on down. Our MEGGER value stayed low and didn't get improved through that process. And that's usually an indication of contamination on our motor. So here we see 2 PI graphs. Here we have a good curve as we measure the current and plot it here. We see it drop, and we see it continue to drop all the way through that test. We do have a bit of oscillation here, which may indicate moisture. but the curve itself looks good. The one on the right, for one, we're at a higher current, and it flattens out here. That flattening is an indication of contamination and moisture. If the motor was clean and dry, then it would be an indication of deteriorated or dry rotted, hard, brittle ground wall insulation. So at this point, we've only done low voltage testing. To go to high voltage testing, then would be the high pot for the DC test. We have the conventional where you raise your test potential up to your voltage up to the test potential, wait for that 1 minute, and it's a go, no go kind of a situation. Again, we're going to look at minimum megohm value where the tester's watching the current, making sure that it doesn't increase rapidly or trip or as an arc detect an arc. So once we achieve that 1 minute mark, we're going to grab our current. We're going to calculate the resistance, temperature correct it, and then compare it to a minimum value. You can kind of do a linear comparison test or comparison to the MEGGER test result to get some linearity, indication of linearity there. However, the step test is the one that really gives you that. Here I've got listed the ramp voltage test, which is actually you ramp up to target voltage, there's no holding, and basically is looking at sustained levels of charging current. And you can see the effects of contamination and moisture in that graph. Step voltage evaluation, again, it gives you a linearity assessment. We're looking at charging current, we're looking at leakage current, and again, all these we can trend by comparison. So high potential test for 1 minute, conventional high pot. IEEE 95 gives us the guidelines there for high pot testing. We're performing a DC high pot test. So the voltage range that IEEE would indicate to take the voltage up to for 4160 would be between 8,800 and 10,600 volts. Our recommendation, a lot of common industries also recommend the two times line voltage plus 1,000 volts. So for that, we would be at 9,300. And so it comes in right there at the middle of IEEE. NEMA MG1 also talks about how high that voltage should be. So it would suggest here in service for a DC test to be at 2448. Again, we would be roughly at 1960 for twice line plus 1,000. So what can high pot testing find? Well, it's going to find that weak ground wall insulation. It's going to be, if you're testing from switchgear, it's going to test your cable insulation. And the other things we're looking for there is contamination level and surface leakage. It's going to give us that information. So you can do the testing either at the motor or at the switchgear. So here is, again, a chart with the test voltages from IEEE, test voltages from AR100, also included here. Step test. So the step voltage test, which is a form of high pot, it would be used in lieu of the high pot, especially if the last step you're holding for 1 minute. That satisfies IEEE 95 and NEMA as far as a high pot test. So we're going to raise the voltage up in steps, holding for the same amount of time at each step. So each raise in or each step in voltage is the same step in voltage for each data point here. So at the end of that 1 minute, we're going to see what our current is. We're going to calculate megohm, we're going to temperature correct it, and we're going to compare to our minimum value. So at each step, we're still looking at that minimum value. The hardware is still looking for any kind of current rapidly increasing, or detecting arc. And it's more than a proof test. So here we're looking for non-linearity indications. So we see one here, and we see that unstable current there at the end. So a non-linear zone would be a little bit higher than test fail zone. And of course, both are higher than that motor fail zone. So it gives us that heads up. It gives us an early warning that that motor is compromised. So our last test here, and I apologize, we've got 5 minutes to cover it, and I will answer your questions if you send those in. I will get to those questions. But last here, I want to look at the surge test. What is unique about it is that it creates a nonlinear drop of voltage across the windings. So now between turns, we do have a difference. There is a drop of voltage across the windings. So it can find those copper-to-copper weaknesses. And effectively, it's a electrical resonance test. So here, as we raise our voltage up and we're pulsing it, we're giving it a pulse. It is a DC voltage. It acts similar to AC, but we're pulsing 5 times a second here and raising the voltage at each pulse. And so as we raise that voltage up, we're getting more and more nonlinear drop of voltage across the windings, stressing that turn-to-turn insulation. And if there is a weakness, the differential voltage will short out a bit of the winding, causing the overall inductance of that circuit to go down, increasing the frequency at which it rings at. So what we're doing is we're taking our tester, we're going to hook up leads 1, 2, and 3 to line A, B, and C. We're going to have our ground lead on, and then we start raising voltage up and pulsing that motor. So the way in which we do the raising, we have a charging capacitor in the tester. We charge that capacitor up. Then we release that energy into the windings. As we release that energy into the windings, it creates electromagnetic field in the winding. It collapses very rapidly and pushes that energy back into the tester, where it creates electrostatic field, collapses, and pushes that back into the windings. And we have this back and forth exchange of energy between the tester and the winding under test, creating that nonlinear drop of voltage across the windings and stressing that turn-to-turn insulation. And so that back and forth response is what we're seeing there in that curve, the surge waveform. And the equation, at least the part that we're interested in here, equation of this waveform, is the square root of inductance and capacitance. So 1 over the square root of inductance and capacitance, and so it's the inductive element that we're looking at for a change in a change that indicates a problem with a failure. So field testing, we're going to look at weak insulation, turn to turn, coil to coil, phase to phase. We are going to, in shop testing with the rotor remove, we can go in a little deeper and look at reverse coils, unbalanced turn count, different size copper wire, all are indications that a motor shop would be looking for. So the way we do that and tell the difference between two waveforms is through the EAR. Basically, we're taking the area of one of the waveforms, the pink part, and we take and divide it by the blue part over there, the area under one curve. That gives us a ratio. The pulse-to-pulse EAR will indicate to us when there is a change or shift in that waveform. And that's what we're looking for, is that shift that indicates to us that we've got a turn-to-turn issue. And that indication is what gives us that heads up about that motor. That's the beginning of the end, as D.E. Crawford said, of that motor. We also have a parameter that we can look at from phase to phase, and if that motor, depending on rotor influence and concentric wound, those waveforms should line up on each other. And if they don't, that's an indication of issues. And so field testing, we would use the pulse-pulse EAR. If we're working off of a motor where the rotors are moved, then we would look at both of those, the pulse-to-pulse and the line-to-line EARs. So again, those waveforms, slight shift, turn to turn, bigger inductive change is coil to coil, huge inductive change from phase to phase. Of course, if they're right on top of you, that's a good motor. So here in summary, we're looking at our testing. Coil resistance is the balance between two phases, looking for manufacturing or rework faults. If you're testing from switchgear, you're going to be looking at connection issues in the junction box. Then we're going to test our ground wall insulation. So ground wall insulation is the low voltage testing, the PI, the DA, the high pot, the step test, ramp test. And then after we've thoroughly evaluated that ground wall insulation, we're going to go to the turn insulation. That's the surge test that gives us that information. And if we find that turn to turn, we're finding the most common insulation failure where it begins. So we're finding the beginning again of that motor. And if we're only doing high voltage, low voltage testing or low voltage insulation resistance testing, then we're missing out on a huge piece of information that we can know about that motor. Again, at the end of the day, what we're looking for is that we know that our motors follow some curve like this because we put it to use, causing that degradation over time. And so we're going to set our parameters and our thresholds of our testing so that we can see when that motor comes into, when its insulation system has drifted down into those switching surges. And that's when we're starting to get failures. And then we know that that motor is compromised and that it's time to switch it out. And we can do it on our time then instead of on its time. So thank you guys. Again, I would entertain your questions. Please send those to, well, through the webinar structure there. If you have questions after that and you didn't get a chance to type them in, you can email me directly. I think I had it on the first slide. And then we do have a survey here at the end. I'll let Meredith take it over.
Yeah, just before you leave, if you could fill out the survey real quick when I end the webinar, that would be amazing. And we'd love to see you at our next webinar. So just head over to us.megger.com/webinars and you'll see the full list there. If you're interested in watching any of the ones that have already passed or this one, again, you can also view all of our completed webinars there as well. So thanks for joining us, everyone. We hope to see you back here again soon.